So hello together. Today I want to talk with you about how to measure the power gain of an RF amplifier. And as building block of our measurement setup, I assume that I have a signal generator, an arbitrary amplifier and also a power meter. And in the first step we will connect our signal generator to our power meter. And what we did now, I sketch here in the equivalent circuit, because all these components are normally connected with coaxial cables which have a certain characteristic impedance. Our signal generator, the equivalent circuit of it will be, of course, consist of the voltage source and of course of an internal resistance which must be equal to the characteristic impedance of the measurement setup. And also the power meter will be, the input impedance of the power meter will be equal to the characteristic impedance of our measurement setup. And what we have here now is that this signal source or generator is matched to the power meter, and the power we will measure here will then be the maximum available power of our signal generator. In the second step we will now connect between our signal generator and the power meter our amplifier. And now I assume that I have an arbitrary amplifier, and if I again set up a crude equivalent circuit, then we have here our signal generator again with an input impedance which is real and is equal to the characteristic impedance of the measurement setup. But in the general case, the input impedance of our amplifier will have a complex value and will not be identical to the characteristic impedance of our power meter. So we will have here a mismatch in the input, and also in the general case it will be like this, that also the output impedance of our amplifier will show a complex value, and it will be not identical to the characteristic impedance of the power meter. And what we measure here is just the power to the load. So we will have a mismatch at the input and a mismatch at the output. And what we define now is the so-called transducer power gain. And the transducer power gain is defined as the power which is given to the load with respect to the maximum available power of our signal generator. So to set up an equation for our transducer power gain, we must first have a look to the maximum available power of a source, which we will describe with the help of the signal flow graph. And if I now consider an arbitrary source, then this source will generate the wave amplitude A0. But in contrast to the first slide, now we assume here that this signal generator will have an internal reflection coefficient, or G. And then we will, to get the maximum available power out of this generator, we must terminate it in the conjugate complex, RG. So to calculate the maximum available power, of course the B2, the wave amplitude B2, will transport a certain power into our termination here, and the wave amplitude A2 will transport a certain power out of the terminal. And so we will get the maximum available power as the difference between this power which enters our terminal and this power which comes out of our termination. And the overall maximum available power will be given then by this equation after some mathematical formulations. The power to the load is much easier to calculate. Also, I assume here that I have the wave amplitude BL, and the wave amplitude AL will describe this power which will come out of the load. And also here I assume now an arbitrary reflection coefficient of the load. And again, if I want to calculate the power of which comes out of our load, I must calculate the difference. And after some mathematical reformulation, we end up in this equation. So we have here an equation for the power of the load, and here we have an equation for the maximal available power, and both equations must be now inserted in this equation, and then we end up in this equation for the transducer power gain of our amplifier. And in the next step we will insert a transistor here, and we will then calculate the ratio BL over A naught. Now I want to go on in the calculation of the transducer power gain of a transistor. And in the first step we use a very simple transistor. We use a so-called unilateral transistor, and this unilateral transistor is defined that we have no feedback from the output to the input. So in this situation, the input impedance or the input reflection coefficient will not depend on the load, and vice versa. So if I sketch the signal flow graph, we have here our generator, which shows a certain generator reflection coefficient. And here we have our transistor now, or our active device. And as you see in the signal flow graph, S12 is missing. So the output and the input are isolated. And of course, we already set up an equation for the transducer power gain, and we now, with the help of the signal flow graph, we can deduce an equation for the wave amplitude which enters in our load, independent of the wave amplitude of our generator. And of course this equation we can set up now, or set into our equation for the transducer power gain, and so we end up in this equation here. And this is a very nice equation in the sense that it can be separated into three terms. One term, which we will call the generator gain, and one term we will call the so-called load gain. And of course G0 will describe now the influence of our active device. And now, since I have these three terms which are independent of each other, I can ask the question under which circumstances, for example, this term becomes a maximum. And then we will see a maximum of the generator gain we will get as soon as Rg is equal to the conjugate complex of S11, and this gives now the maximum of our generator gain. And of course, on the other hand, I can also calculate now under which circumstances the load gain becomes a maximum, and then we also see that the load gain will become a maximum as soon as the load reflection coefficient is equal to S22 conjugate complex, and this again gives us the maximum. So now these two conditions already define us now the setup of an RF amplifier as soon as we have a unilateral transistor which is stable over the whole frequency range and which has no feedback from the output to the input. Now we are ready to discuss the principal setup of an RF amplifier as it results from a unilateral transistor. A unilateral transistor means that it has no internal feedback and that it's absolutely stable. In this case, we saw that if I have the active device and if I want to have a maximum in the power gain, I have to have that the load impedance must result in a reflection coefficient which is equal to S11 conjugate complex, and the same is true for the load impedance. Also the load impedance the device wants to see as 2-2 conjugate complex. But if I have a 50 ohm system, we will always have here a generator impedance of 50 ohm, or we will have a load impedance of 50 ohm. So we must use a lossless matching network or a lossless input matching network to transform ZC into S11 conjugate complex at the frequency of operation. But this is equivalent for the case that I transform S11 at the frequency of operation so that the input impedance I see in this lossless matching network is equal to ZC. And of course the same will be true for the output. Also the output, the active device wants to see as 2-2 conjugate complex at a frequency F0 if I see into this part of the circuit. And so we have to use a lossless output matching network to transform ZC into S22 conjugate complex. But this is equivalent to the point that if I have a look into this part of the circuit, that the output impedance at the frequency F0 must be equal to ZC. And if we do this, then we end up in the so-called unilateral transducer gain, which means this is the equation which depends only on the S parameters of the transistor, which I use, and I can in principle can calculate the possible transducer, unilateral transducer power gain. But in practice, even though S12 is quite small, it never will be exactly to zero, so we have to also to consider the more complicated case, and this we will do next. I will now consider the case of a so-called bilateral transistor, which means we assume now that S12 will be not equal to zero, and this is normally the practical case. S12 will never be equal to zero. And of course then, if I sketch now the signal flow graph, this signal flow graph will become far more complicated because of the feedback inside our transistor, and instead of having only 2 loops, we now will have 3 loops. This means the output reflection coefficient will have an influence on the input reflection coefficient I see in our transistor, and the generator reflection coefficient will have an influence on the S parameter S22 or on the scattering parameter I see into this network. So it's now far more complicated, and so I can only summarize the result because the mathematics are quite lengthy here, and we will find, or if you go through the theory, then you find that the input, the optimum input and output matching will be only possible if really the transistor is stable. So a prerequisite to set up an RF amplifier is in the first case to stabilize the transistor over the whole frequency range. And as soon as it's stabilized, then we can calculate the so-called maximum available power gain. This expression, and you see here, this expression is true or is possible to calculate as long as k is greater than 1, otherwise this makes no sense. And so this maximum available power gain is now the gain which you can in maximum get out of a transistor. And to get a crude approximation for the case of an unstable transistor, we define the maximum stable gain. This maximum stable gain is just defined by assuming that k is equal to 1, and there is no question how did we reach this value, but if you see, as soon as I have k equal to 1, then this is equal to 1, and we get the so-called maximum stable gain. So we have now two further parameters which we can calculate for a transistor. We always, as soon as the transistor is stable, we can calculate the maximum available power gain, and if it's unstable, we at least can now calculate the maximum stable gain, and of course this is also implemented in the simulation tools.